Okay, so our speaker is Anthony Alaribe, I'm sorry. And he'll be talking about teaching computers to detect API bugs and incidents in production. Anthony is a staff software engineer at Delivery Hero, where he builds software to help get food to hungry customers. In his own time, he enjoys exploring how to make our work as engineers more efficient through new and old technologies. He loves hiking and cooking dishes from other cultures. So take it away, Anthony.
Thanks for the intro, team. I would share my screen. Okay. Please tell me you can see my screen.
Yes.
Oh, awesome. Thank you. So thanks, team. So like Tim said, my talk would be about how we can teach computers to detect problems in production. So, I mean, Tim did a lot of these intros already. I would just add that you can reach out to me on Twitter. You can follow me, send me a message. I'm always curious and interested in talking to, to people from the community. So I would just jump in. So this is my Twitter handle if you want to message me. So this talk, you won't see a lot of code. It's more of a thought experiment and a bit of a tease. And the whole entire goal of this talk is basically to encourage us to rethink how we treat our APIs and encourage us to basically treat them as data, analyze them, get insights from them, and prevent a lot of issues through this analysis. So to jump in, I always say what separates a senior engineer and a junior tends to be how much issues and how much bugs that the senior, for example, has experienced in production. Because no matter what kind of systems we build, it's almost a standard in our industry that things will go wrong. If something can go wrong, it probably will go wrong. And as an industry, we've come up with a lot of strategies, a lot of workflows for dealing with this. But I would start by discussing the type of bugs that are common. So there are implementation bugs. Implementation bugs are basically when we have a specification to implement a functionality in our software, but we just make a mistake, or we misinterpret the specification, or we make a change in the software that ends up affecting something completely different, especially in legacy systems where maybe you're a new engineer in the code base, you don't fully grasp the effect of every little change you make. And this is a very common cause of bugs in production, that someone made a change and it affected something completely different from what he intended to change. Another kind of common bug would be specification bugs. And this is a situation where the implementation is correct, but the implementation is based off assumptions that were made when designing the system or describing the problem that needs to be solved. As a rough example, say we have a specification to implement an adder that adds 2 + 2 and it's expected to return 5. Let's assume that's what the specification says. And you implement this function. When it gets 2 + 2, it returns 5. But in the real world, your customers expect something different. They expect that 2 + 2 is 4. So even though you as a developer implemented precisely what you were supposed to implement, what was specified, it could still be a bug. Another kind of issue would be unspecified workflows. And these are very common because I like to say what you don't know, you don't know. And this is usually where you design a system and then in production or while the system is running and doing what it's supposed to do, new use cases or new ways or people just use your software a little bit differently from how you intended, or just problems that you did not expect to happen just happen. For example, you implemented, I don't know, a software or a system that saves, that holds account balances, and you use an integer, let's say integer 64, probably something smaller, let's say integer 8. And then someone like Jeff Bezos moves his entire account balance into your system. And now the integer value you have can't hold his account balance anymore. So this was probably a use case you did not picture. You did not expect that someone with so much money would use your system. So it just makes me laugh when I use this example. So this is an example of an unspecified workflow. It's a workflow that it just came up in the course of using your software. There's also infrastructure bugs. Cloudflare could go down, your database could go down, I don't know, your network could be congested. Just so many things can happen. Your data center internet could just go down. And sometimes this kind of infrastructure issues, you can't predict them. Maybe you can add some fail safes, like having redundancy, cluster redundancy, different kinds of redundancy, but they happen. And as an industry, we have different techniques and strategies for working around this. Another kind of issue is basically nature's middle finger. And I add this example because no matter how much we plan and try to mitigate all the other kinds of bugs and issues I mentioned, you have the perfect specification, you have the perfect implementation, you have so much redundancy and fail safes in your infrastructure, things could still go wrong. And this is an example of where the universe just decides to give the middle finger to our software. And it's a common case called a cosmic bit flip, where neutrinos, or just particles that are all around us from the stars, could toggle a bit in our RAMs, for example, or just in our systems. And there's so many examples of issues which have happened, that bugs that just appeared as a result of cosmic bit flips. It's even common now in systems that very, very critical systems to implement workarounds for this. For example, in the International Space Station, they would have multiple servers executing the exact same code. And when something goes wrong, or not even when something goes wrong, all of these servers implement the exact same code, and they use a kind of consensus to decide which results to take. So if you have 5 servers and four servers return the same value, one server returns a different value, then of course you would go for what the 4 servers returned, because maybe that one server that returned a different value, you did that as a result of a cosmic bit flip, for example. And there are many examples of this. Even Google, there's a famous Google issue where Google's, in the early days of Google search, the search result had a bug, and Sanjay had to dive into the generated binary to identify the issues. But these are things you can read about. There's a nice YouTube link here which you could check out to just watch more about this interesting topic. But moving on, how do we prevent and detect bugs in general? We know that bugs are almost inevitable, but that doesn't mean we should just give up and allow the bugs to happen. And as an industry, we've come up with different techniques. For example, types. Contrary to what you would think, types are a very common and very useful strategy for preventing a huge class of bugs, just because they catch silly mistakes, like marshalling and marshalling mistakes that could have happened due to typos in maybe your field names, could be caught if you're using a strongly typed system, like Go, for example. Another very common approach is that teams tend to write a lot of tests, unit tests, integration tests, basically all forms of tests. And how these tests work is that you define a given set of example inputs and the expected outputs given those inputs, and then you write a test to verify that for this input, you would always get these outputs. And this is a common strategy, it works. And another relatively more maybe common strategy would be property and fuzzy testing, which just got into Go recently. But property testing as a topic has been around for quite a while, especially in other ecosystems. And this is basically where you define the property of, for example, your function or your system and say this system is supposed to behave like this. And then the property test framework generates like a lot of random inputs to verify that, for any random input that fits that property which you've described, your system the way it's supposed to. So, for example, specification, and it's quite useful. Another common strategy is benchmarking and load tests. Sometimes your system just crashes because it gets too much load. Maybe you implemented an algorithm that made assumptions on, for example, how much resources are available. So teams load test these new, new implementations or new algorithms before they roll them out to production, just to make sure that their system can handle their production traffic, in the real world. Another strategy would be chaos engineering, which is where you manually just cause issues to happen. Usually this could be by maybe making a server go down, making a database go down, just to verify that your system can recover and handle these issues correctly. This last point, it's a bit different from the others, and it's more about the question of, we have all of these different strategies, but sometimes it's important to also think about the systems that we are building. For example, not every system is critical. So there are two different mindsets we could have. If you're building a system where it's not the most critical, maybe you can implement some of these strategies, but have the mindset that things will break. And it's more important to detect when these things break very quickly, learn from them, evolve, and move on, very quickly. While the other mindset is just being very critical and pre-guessing all the issues that could happen and preparing for those issues before they've happened. So I imagine for a lot of systems, it might be more beneficial to have the mindset of just being prepared that issues could happen and being ready to detect them quickly and just evolve and move forward as fast as possible. So I would move on. There's another strategy which I didn't mention in the last slide. And I'm going to get there. But the strategy asks the question that, so detecting problems seems to be very important because we know that problems might happen. So what if we could teach computers to spot these issues and detect them maybe immediately they happen? And the reality is that as an industry, we already do this. If you've used that, for example, you probably that for some metrics, such as your latency, that's your response time, or your throughput, which is how many requests per minute or per second you're handling. It's able to monitor this, and when something changes, when it knows what this graph is supposed to look like, and if the graph changes, then that means something is wrong, and someone should be notified. So these strategies of using computers to detect issues already exist. But what if we could leverage it even more? And that's much of the point of this talk. And the reason is that APIs, they are contracts. We usually have requests, we usually have responses, but they tend to, it's a contract. So we define a shape which we expect the users of our APIs, for our systems to satisfy. And this shapes, finite responses, at least for the shape, with all the keys that you expect from your clients. So computers are very good at detecting patterns. And so what if we leverage these computers and make them detect patterns, not just on how many requests per second we're handling, or what is the response latency, but also on the shape and the contract that we are exposing. So this is an example of an API. I mean, not a complete example, but so we have a post request to this endpoint demo/payment. And in here we have an amount. As a human, you can look at this amount and see that even though this amount is a string, it's pretty much a number. It's 75. It's a number, but it's wrapped in a string. You can look at the receiver and see that, Jeff Bezos, that has to be a name. You can look at this card number, and if you come to and the same thing for pretty much all of these fields. So humans are good at noticing these patterns, but unfortunately, you can't put a human to look at every single request and response combination, leaving your coming in and out of your services. But if we change how we look at this, some things become a bit easier. For example, if we flatten that API, the same API we looked at before, we get something like this. So our API becomes a sort of a key value pair, pretty much. So okay, let's come here. We know that payment UUID is this, payment amount is 75, payment receiver, this list, the name is Jeff Bezos. So now we have a key value pair of that represents one request that comes in and out of our server. We can do a lot of things with just this representation. For example, if we look at not one request, but look at a series of requests, pattern emerges. For example, you can, just by looking at this is just for the response, you see that status is pretty much always a Boolean. It's true, true, true. Maybe sometimes you get a false. So this is a pattern. This, if you maybe plot this in a graph or in a pie chart, you would see that, okay, 70% of the time, maybe it's a true, and the other percent of the time it's a false. The same thing with the message. You can see that, okay, sometimes we always get payment sent, sometimes we get payment failed. And as a human, if you look at this and you see a no, it rings bells. Why is there a no here? This is a bit different from, all the other examples of messages that we've been getting. So this is a pattern that computers could be trained to identify. So if you take this series, for example, and train for example, to spot these outliers. Not even without a machine learning model, if you just group this, with regular statistics, it becomes easy to see these outliers when they happen and raise bells. But before I go into those examples, let's just move in first. But this concept here, it's not really so special. I mean, you could for example, plot the same graphs by logging this information in your charts, but this information is in your APIs always. You would always have your amounts inside your APIs, and you could as well just analyze them. But let's go into some benefits. So treating this API requests and responses as data opens a whole new playing field. And this is something we don't do for some reason. We don't really see this in and out as data that could be analyzed. And just by analyzing, for example, with the payment amounts, if we look at this series, sorry, I'm in the wrong screen. If you look at the series 75, 50, it's easy to raise flags if a new engineer on our team, maybe he was writing code, he did not look at the existing behavior and decided to return a $sign as part of the amount. You know, he had good intentions, but this breaks the API contract. If we had some I don't know, machine learning algorithm or just someone looking at all the APIs, if that's possible, it would be very easy to flag that this is wrong, or that this 50, which is now an integer and no longer a string, is pretty wrong, or that we should not be returning the first name, you know, as an amount. So this becomes one big use case. So I add some screenshots from, I didn't mention it earlier, but the API Toolkit project, which I was. So another thing we could do by analyzing our requests and responses is that it becomes possible to model relationships in our endpoint. For example, we can notice that every time we have this X field, we always get this kind of response. Or maybe anytime someone tries to initiate a payment transaction on our endpoint, we always return a failure response. So this is an easy relationship that we can, you know, throw into a kind of graph representation. And if in the future someone sends a request without an amount, and then we don't return a payment failure responses, then it means this shape which we had learned, which our machine learning algorithm, for example, had learned, is broken, and someone could be notified and alerted. Another thing we could do by analyzing this request as data is that we could generate metrics just based off this request and response data. For example, if you want to, say, have a chart that represents how much your users are sending, you know, every day, probably what you would do is go into your database and, you know, query this from your database. But you could also do this, or maybe log the data to your logs and use your log. If, for example, if you use Datadog or Grafana, try to chart it in there. But this could require extra instrumentation. But since the data is already in your requests and responses, if you're already analyzing this data, you can generate a dump, put it into your Python, you know, library, and just plot it. So this is an example from also, yeah, I would not say where it's from. Something else that becomes possible is that you can learn your API, you learn these shapes, you learn the formats. This makes some things possible. You could generate documentation just based off this data that you're learning. And if you are, you know, running this on production data regularly, then you could easily have some form of documentation that always mirrors your production state. So taking out the issue where Swagger files are out of date, etc. Of course, you can do other things like, you know, if you're exploring this data, you can have real examples of what each of those fields should return. And maybe also use that to enrich your documentation, for example. or plotting your graphs, showing, like for example, you could draw a pie chart that shows the representations or the different currencies in your system. You know, if you, maybe 70% of the currencies people are using for transactions is USD, and 20% is, I don't know, pounds or something. You know, you can model these representations just off your request and response data. So what's the point of all this? The point of all this is that issues happen, bugs would happen, and it might be a bit beneficial to have the mindset of preventing them if possible. As you know, maybe sometimes you try to prevent, you write a lot of these tests, but it's also equally as important to invest a lot into techniques to discover when the issues happen, recover from them, learn from them, and evolve as, you know, as a system. It's important to put thought into this discovery, but also invest in automation. And there's a lot you can do with automation, and there are techniques that as an industry we're already doing. For example, blue-green deployments, where you push a change to production, something you instrument and monitor, so that if a KPI that is being tracked drops, for example, if the number of orders per minute that you handle as a system drops, then maybe something is wrong and you can automatically roll back, you know, your deployments. So leveraging all the monitoring you can have can be maybe even more useful compared to trying to predict every single incident that could happen, because to be honest, more incidents would happen which you did not predict. Also, it might be very, very beneficial to leverage a lot of these new technologies. You know, we developers use machine learning, data science. We use all of these tools to solve problems in other domains, to solve fraud, to solve, you know, just name it. Maybe it's about time we also leverage those techniques to solve our own problems. So we can look at our services as data, we can analyze them, and we can just be prepared for when issues happen. So this was this is the end of the talk, actually. A lot of the screenshots in the project are from a lot of the screenshots in the talk are from a project that I'm working on called API Toolkits. And the idea is basically to leverage some of these things I'm talking about, trying to analyze API data, detect when things change, when something goes wrong. But the truth is there's a lot of insights that could be gotten from API data. And it really surprises me that more developers are not actively analyzing this request response data. And so I implore all of you here to try it out, you know, generate a dump of your production traffic. Maybe you can you know, strip out the sensitive data, and clean it up into any tool you're using analyzing data, and try to see what metrics you can get. And also, just if you have ideas for tools, this is a space where, you know, just explore those ideas, build these tools. Let's have systems that, you know, let's just be analyzing this our data. Okay, I think I stop here. But thank you. If you want to explore some of these things even more, you can check out the API Toolkit project, or you can send me a message on Twitter. I shared my Twitter handle earlier. I'm always open to conversations about these kind of topics. So thank you.